So if you've ever been fascinated by top fuelers, nitromethane, the raw power, anything like that, you've landed on the right video because we're going to break it down for you and explain what's going on there. Where's all this power coming from? What's happening? What exactly are you looking at? So let's get into it. To the digital board of knowledge. So why don't you see this a lot in like local garages or anything like that? And that is because it is a battle of cost attrition. It's insanely expensive. When they go down the track, they have to completely rebuild the engine, replacing a bunch of parts. They have to have a specialized team on hand. And that's if they don't get a blower bang. Because nitromethane is always riding on the edge of hydrolock. Should they get a blower bang, their custom block, $60,000. Blow off a cylinder head, $10,000. Launch a supercharger into the grandstand, $15,000+. That's how fast this adds up. You cannot run a nitro car unless you have $1 million race team behind you. That's just, at the end of the day, that's what's going on here. So what are we looking at for the fuel? Gasoline, because here's the paradox, right? Gasoline actually creates 114,000 BTU per gallon, right? Nitromethane creates 28,000 BTU per gallon. So that's 4 times less energy inside a gallon of nitromethane over a gallon of gasoline, but yet just switching over to nitromethane on the same exact boost, you get 2.3 times more power right out of the gate. What's going on here? Why are you getting more power when it has less power? What's happening? And that is because the nitromethane molecule is CH3NO2. That's 52% oxygen by weight inside of it. So that means it's bringing its own oxygen to the party. This is what the molecule actually looks like. This is a gasoline molecule. Carbon, hydrogen, you know, that's how it goes. You don't see any O's in here, which is your oxygen. Now nitro, you got H, C, N, and then 2 oxygens. So what are we looking at here? When you're switching over to nitro, your baseline, what's going to need it for gasoline is 14.7 to 1. So that's 14.7 pounds of oxygen for every 1 pound of fuel. That's how it breaks down right there. With nitro, you're switching over to an ultra fat 1.7 to 1. So that's 1.7 pounds of oxygen per 1 pound of fuel. So you almost need pretty much no extra air. That means you can jam 8.6 times more liquid into the cylinder. So yes, it has 4 times less power, but that's how you double your power immediately because you're putting 8.6 times more liquid inside of that cylinder. Now, static compression, this is one of those weird things at nitro it's cool, right? So your baseline street gas or E85, depending on what you're running with, gas are going to be around like 11 to 1. E85, you jump that up to 14 to 1. And the reason you do this is because you're squeezing the air. The more you can squeeze the air-fuel mixture, the bigger the bang you're going to get. So you want to squeeze it as much as possible without running into pre-detonation. Nitro, you have to take the opposite approach. You have to drop it down to 6.5 to 1 or 7 to 1 static compression. This way you have more room, which I'll explain a little bit more later. But a street engine, you're trying to compress as much air as possible without having to detonate. Nitro, you're trying to create more room to be able to handle all this liquid. And the reason is, when we're talking about actual liquid, you're making room for 37% more liquid fuel inside of the oxygen, inside of the air mixture. So, what does that look like? So your air tank mixture, let's go and pretend the whole thing is 2.7 pounds. That'd be 1.7 pounds of air and then 1 pound of fuel. So gasoline, when we're talking about how much it's actually taking up here, so on your gasoline with your 14 to 1, that'd be 1 pound of fuel, so the whole mixture would be 15.7 pounds. You're looking at 6.3% being fuel by weight. On your nitro, you're looking at, out of 2.7 pounds, 37% being pure liquid fuel. So you're basically trying to flow a swimming pool where with a gasoline engine, it's mostly oxygen. So how does that break down? What's going on here? Why the less static compression? Basically, with your 6.3% with fuel, the actual volume of liquid inside of this cylinder is only 0.1%. So you can take that, since it's mostly air, and you compress it to the point of where it would detonate. That's where your limit is. Well, with nitro, at a weight of 37%, that's 8.6 times more liquid, you're going to be operating between 5 and 10% actual liquid inside the cylinder. So let's pretend this is your cylinder, right? 5 to 10%, depending on how they're on the throttle or where they are on the track, is going to be liquid. That's before it compresses. So why does that matter? So let's pretend I had 10 to 1 compression, right? That means I'm taking the whole cylinder and I'm dividing it into 10 equal places, and I'm compressing it into one of those 10 places. So that means if I'm running 10% fuel, liquids cannot compress. That's not how they work. So if I'm running 10% fuel and I have 10 to 1 compression, as a piston comes up, I run out of space and I pop the head off. So you have to drop it down to, like, again, 6 to 7 to 1, so you have room to handle that 10% fuel. And you're always right on the edge of hydrolocking, and that's the problem with it. 6.5 to 1, that's typically a good compression ratio because you need the room. It's all about creating room for that nitro to go in there. Nitros, they flow a lot of fuel. So in a single pass, you're looking at 15 gallons of fuel. That's up to 100 gallons per minute. That liquid does not compress, especially at 8,000 RPMs. So if you're running too much compression or something goes wrong with the engine, well, now you get into hydrolock and you pop off your piston. Not a good idea. That's not awesome at all. Your piston's going to slam into a bunch of fuel, and because, like I said, fluid can't compress, it's got to go somewhere. So your head's coming off, your rod's bending down like it's a toothpick. You could blow out the side of a wall. There's just a whole bunch of different things that can go completely wrong. Now, another cool thing about nitro that a lot of people don't understand is the ignition timing. So for gasoline on a street engine, you typically start off about 10 to 15 degrees before top dead center. As you're accelerating and you're going to advance the ignition because you've got to give the fuel time to burn. So you're accelerating, well, now you're going to bring on the spark earlier, you're going to bring it to like 20 to 32 degrees. This way the spark can hit, the fuel's got time to create its pressure wave, and then push down on the piston. This way it's not creating the pressure wave while the piston's halfway down, because you want to take advantage of that. Nitro is the exact opposite. So you're going to start with a wild 50 to 55 degrees before top dead center because it burns really slow. So you need a lot of time to get that fuel burning. Now as you accelerate and the boost comes on, it actually changes. Now the burn time decreases. So what you have to do is you have to retard the timing to 38 to 40 degrees before top dead center, which is still wild. That's still like way more timing than a gas engine. But the point I'm saying is here is now you're going in reverse. As you're accelerating, the RPMs are coming on, you're pulling back the timing. Where on a gas engine, as you're accelerating, the RPMs are coming on, you're adding timing into it. So that's just kind of a weird little factoid about it too. Now we got CAM, the LSA. This is your overlap. On your standard street, like earth-shattering, like boom, 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 boom engine, you're going to be looking at like 106 to 110 degrees of overlap. This is because you're going to want scavenging. You want the intake and the exhaust valve to be open at the same time, so all the stuff going out of the exhaust, well, before that exhaust valve closes, the intake valve opens up so it can catch a ride on that train and fill that cylinder up with new air and fuel. You absolutely do not want that on a nitro engine. Your LSA is going to be like 114 to 116 degrees. You want a physical wall separating the hot exhaust from the incoming fuel, otherwise it'll just run in reverse. It'll set your blower on fire. Boom! You have a compression inside your blower, blowing apart your blower, just completely shattering the engine. There goes like $100,000. So not good at all. Overlap on the street, that's free horsepower. Overlap in a nitro, yeah, that's a bomb. One backfire, it's game over with. You do not want overlap with a nitro. And another cool factoid is there's actually more aggressive on the exhaust side. So the exhaust will open up, well, it's still on the compression stroke. So there's time to start pushing that out because let's pretend you went, all right, so here's the compression stroke. We got, boom, the nitro detonates, the piston's going down, going down, going down, going down. If I don't open that exhaust valve early and start venting off that pressure, when the piston has to change direction and start going back up, especially at 8,000 RPMs, it's still building pressure and pushing down. Exhaust valve open or not, we have a problem. So as the piston's going down, when it's getting close to the bottom, boom, they're going to open up the exhaust valve and they're going to give the exhaust valve a whole bunch more lift and duration than you would on, say, a street engine where you're going to favor the intake side. On nitro, you favor the exhaust side. So you open up the exhaust valve, start relieving the pressure, so when the piston gets to the bottom and it has to change directions, it doesn't still have a whole bunch of pressure pushing down, so it can actually change directions without blowing the motor to pieces. Wild factoid about nitro I didn't know about until I started researching this topic. Alright, so there's the exhaust report card. For E85 or fuel, you're looking for a clean burn, basically an invisible flame. If you have a flame coming out of exhaust gas on E85 or gasoline, yeah, that's a problem. Something went catastrophically wrong with the engine. With nitro, you're going to want the burn. Because it burns so slow, it's coming out. Basically, the nitro engine is going to burn until it runs out of oxygen inside of the cylinder, and then you're going to dump, not raw nitro, but like oxygen-less nitromethane into the exhaust pipe, and then once it hits the atmosphere and it hits all that oxygen, then it's going to reignite again. So that's why you're going to see your huge, massive flames. They can actually judge how well the engine is running by the color of the flame. For example, if you have a bright white flame, yeah, that's a meltdown warning. Your engine is literally melting itself. You're melting cylinder heads, tops of pistons, valves. That engine is in meltdown mode. A good, healthy one, you're going to get a nice, bright yellow and a crisp orange. That's the sweet spot. That is a perfectly healthy nitro engine. Again, it's just unburnt nitro vapors and CO2. It's hitting the air, and that's where you're getting your two different colors from. The nitro color and the CO2 vapor, that's your two different colors. That's where you're going to get your bright orange and your bright yellow. That is your sweet spot. It's just reigniting once it hits the atmosphere because it's burnt everything out of the cylinder. And now it gets a fresh dose of air. When it hits the atmosphere and it's so hot, it just sets off and goes again. Again, bright white is bad. That's your meltdown warning. Green, that's really, really bad. That engine's going to hydrolock. Green means that there's still a whole bunch of oxygen left in the fuel. That means the fuel is raw and unburnt. You're not putting enough oxygen in there, or a spark plug went out, or green's bad. You don't want green at all. That means you're about to pop off the top of a cylinder. You're going to drop a cylinder soon. You're going to blow a head off. You're going to have a detonation. Green. Okay, there's green. Boom! Now you have your explosion. There's not going to be a whole bunch of time there. Maybe if somehow they have a remote shut off, they can shut it off in time. But pretty much once you see green, well, get ready for the explosion. Yeah, you don't want green. You don't want white. Here's a couple of examples. Now, I didn't take these photos, so I don't know if they've been color corrected or anything like that, but they do illustrate what we're talking about here. Now, here we have a nice orange, a nice yellow. Got your orange and yellow colors right there. This is a healthy engine. This has got a good burn on it right here. This engine is running great. It's got a good air-fuel ratio, good timing. Everything is running fine. Here's just completely white. A little bit of orange and yellow, but mainly this is white. So this engine is melting down. You are currently melting parts inside. Maybe you got too much timing on it, maybe too much air. I don't know what exactly the problem is, but this is not what you want to see. Here's your greens. Notice there's a really small flame, a whole bunch of green in there. This engine's about to hydrolock and blow off a head. Again, like I said, I didn't take these photos, so I don't know if these have been color corrected, but they help illustrate the point. This is what you're looking for. You don't want green, you don't want white, you want orange and yellow. All right, now the whole diesel mode. So this was kind of confusing to me because if these engines are so on the ragged edge of hydrolocking, what happens when it enters into diesel mode? And essentially what happens is this creates so much heat and it's so violent, it will actually melt away the spark plugs and the ignition leads. Everything will be gone and it will be strictly operating on diesel mode towards the end of the track. That means that it's no longer using ignition to fire. Basically, it's coming up and it's using all that temperature inside the cylinder, and that's what's determining when it's going to fire and when it's going to go. So I thought, oh, this must mean that hydrolock doesn't happen anymore. No, absolutely wrong. So you've lost total control of the timing. You're just relying on it to fire whenever it wants. And when you hit this mode, you can eat through pistons and valves very quickly. So let's pretend you lose compression on a piston because you eat through it. Well, yeah, you know what happens then? Well, now it's not got enough compression to detonate it. Now you get into hydrolock, boom, blow it off. Same if it decides if there's too much heat, it starts detonating early. Also, you're going to notice that in nitro cars, you're going to have that milky oil that you would see when, say, your head gasket goes out in a normal car. Well, this has nothing to do with coolant because, yeah, coolant's not even a thing. But what's happening is the nitro is going past the rings because there's just so much in it, and nitro is a solvent. So it's going to remove the oil's lubricity almost immediately. And that's why like they have to completely rebuild these engines. Well, aside from the fact that they're burning out rings, they're burning out spark plug wires, they have to go through everything, they have to replace any bent rods or anything like that. Yeah, the oil's also shot. Anyways, this is a little bit of what's going on with nitro cars. Helps you kind of get up to speed, so when you're watching a nitro race or something like that, you can see what's going on. You're like, oh, that's a green flame, that thing's about to explode, or that's a white flame, that thing's melting down. Then you can see like, the yellows and the orange, you'll be like, oh, that's a nice healthy one. Then you know what's going on with the dieseling and all that. But yeah, appreciate you guys watching my video. Hope you found it educational, maybe just a little bit, or maybe even just a little bit entertaining. Anyways, if you'd like to help support this channel, make sure to click on that Amazon affiliate link in the description. Even if you don't buy what that link is for, just clicking on it. Doing the Amazon shopping you were already going to do anyway, I'll kick back for it because you came there off my channel. Thank you for watching. Don't forget to subscribe.